Actually, no, I can almost certainly tell you that you won't be in the starting spot.
I mean, yeah.
All right.
Bro.
Number 1 is C.
Yep.
Dang.
Number 2 is D. Number 3 is 0.6. Number 4 is 1.03. Number 5 is 16x minus 5y over 5x plus 3y squared for part A. For part B, y equals negative 1 plus 3 times parentheses x minus 4. And C is negative 0.4. For number 6, for part A, it's 100. And part B, y equals 20 plus 3/5 x. Number 7, for part A, it's 6.234. For part B, either 0.669, bless you, or 0.670. This is an under approximation because since f double prime is positive, the function f is concave up, meaning that the tangent line is below the function at x equals 3.1. Number 8, the equation would be y equals negative 4 plus 5 times parentheses x minus 1. F of 1.2 is approximately negative 3. And the approximation is less than f of 1.2 because f double prime at 0 is positive. Therefore, the tangent line is below f of x at x equals 1.2. For part B, the average rate of change, let's see, find the real positive number. Okay. R equals 6 is the answer. Since the average rate of change of f prime on the interval from 0 to 0.5 is 3 minus 0 over 0.5 minus 0, which is 6, and since f double prime exists for all x between negative 1.5 and 1.5, and f prime is continuous on the closed interval from negative 1.5 to 1.5, and differentiable on the open interval from negative 1.5 to 1.5, we can apply the mean value theorem to f prime, which means there must be a c value between 0 and 0.5 where f double prime is 6. For part C, when you take the derivative, g prime is equal to 4x minus 1 for x less than 0, and it's equal to 4x plus 1 for x greater than 0, and it does not exist at x equals 0. Since f double prime is greater than 0, that was given in the original, I believe, in the stem of the problem, it is not possible, but g double prime at d does not exist at x equals 0. It's not possible that those two functions are the same. All right, questions?
Number 6.
Number 6, all right. All right, so line L is tangent to the graph of E at this point, as shown in this figure. Find the x-coordinate of Q. All right, so Q has coordinates x, comma, x minus x squared over 500. All right, so we can find the slope of this line two ways. We can find the slope by just doing the slope of a line, change in y over change in x, and we can say that it's equal to the derivative of this curve at this point. So the slope would be the change in y, so that would be x minus x squared over 500 minus 20 all over x minus 0, or just x. So I'm going to go ahead and simplify that. That's 1 minus x over 500 minus 20 over x. You know what? I probably shouldn't do that. Never mind. You can do that, but I think it makes it worse. And then y prime is 1 minus 2x over 500, or 1 minus x over 250. So did you set those two equal to each other?
I didn't do any of that. I did something funky that's completely wrong. So no, I did not set those equal to each other.
So this is like the one we did the other day in the notes, where we had a line that went through the origin and was tangent to natural log, find the x-coordinate. It's very much like that. So setting those equal would be 1 minus x over 250 is equal to x minus x squared over 500 minus 20 all over x. That's just all kinds of horrible. I would probably multiply both sides by x. And then I would probably put that into my calculator and see where those two are equal. Oh, I can drop off the x's. Oh, this may not be so bad that I can't do it by hand. So this would be negative 2x squared over 500. Oh, I can do this by hand. This isn't so bad. Equals negative x squared over 500 minus 20. So negative x squared over 500 is equal to negative 20. So x squared is equal to, what would that be, 10,000? So actually be the square root of 10,000, which is 100. Problem is, if you didn't find that, then finding the slope was really, really, really hard.
Yeah.
You're good from there?
Yeah.
Okay.
Just on the homework in general, like before, you see how before the question says AB6?
Yes, that's just telling you that where it came from. It was on the AB exam, and it was a question number 6 on the free response.
Oh, okay.
That's all that's telling you, because Ian doesn't like it when I number them with the numbers from the test. So what's happening is, if it's because these are all taken from the time before they switched to 2 where you could use a calculator and 4 where you couldn't. On all of my worksheets, if it's an A, B, or BC, number 1, 2, or 3, you can use a calculator. If it's 4, 5, or 6, don't use a calculator on those. Okay? That's just generally speaking, anytime we've got worksheets and stuff. So this was an AB6, so this had to be done without a calculator. Okay? Yes, sir.
Number 2.
Number 2. All right, so this is a calculator active problem, obviously. Let f be the function given by f of x equals this quadratic. The tangent line to the graph of f at x equals 2 is used to approximate values of f of x. Which of the following is the greatest value of x for which the error resulting from this tangent line approximation is less than 0.5? All right, so the error is going to be the difference between what the tangent line says it is and what it really is. Okay, so to find the tangent line approximation, we know that f at 2 is equal to 3. That's a pretty easy substitution. And f prime of x is 2x minus 2. So f prime at 2 is 2. So our tangent line approximation is y equals 3 plus 2 times x minus 2. Okay? That's the tangent line approximation. This is the actual value, right? The function is the actual value. So the error is the absolute value of the difference between the two, and it really doesn't matter which one you do first. Let's simplify this a little bit first. That's going to be a negative, so it'll be 2x minus 1. So this will be minus 2x plus 1. So the error is the absolute value of x squared minus 4x plus 4. And we want to know, when is this tangent line approximation what is the greatest value of x for which this is less than 0.5? All right, so I'm going to graph this error function. Get rid of these. So I can never remember the other place where absolute value is. So x squared minus 4x plus 4. And I want it to be less than 0.5. So I'm going to graph y equals 0.5 also. And I'm going to just go between, I'll usually go a little bit further to this side to the left and a little bit further to this side. So I'll go, I don't know, 2.2 to 3 with my window. And I don't want to go negative 10 to 10 because I'm only looking for where it's less than a half. So I'll go negative 1 to 1. Part of what you're expected to be able to do on the AP exam is graph things in a window that make it easier for you. All right, so that's where they're equal to each other. And it would have been smarter, hang on just a second, on my window. If I went 2.2 to 3, I probably should make my step 0.2. So there's 2.2, 2.4, 2.5 would be there, 2.6 would be here, 2.7 is here, 2.8, obviously at that point this one's higher, so I think it's at 2.7, and I believe that's the correct answer. Okay, so anytime you see something about error, it's the difference between what you estimated and what is the actual. And it's always absolute value because it doesn't matter whether the estimate is too big or too small, the error is the difference between the two. Error is always positive, sort of like distance is always positive. Number 7, okay. Any particular part?
I find the formula for the A, but I got the wrong answer.
Okay, so let's see.
Y equation is 6 plus 211.
Wait. 6 plus what?
0.211.
I have no idea. I didn't put in. You said 0.211?
Yeah.
Let's see, 1 plus. I didn't do it as a decimal approximation because I never approximate anything until the end of the problem. No, the slope should be 2.342.
That's the problem.
All right, so let's find the slope. So it gives you the derivative already, right?
Yep.
So the slope will be 1 plus e to the third over 3 squared. I just left it like that. So then my tangent line approximation is going to be y is equal to, we know the y coordinate was 6, plus 1 plus e to the third over 9 times x minus 3. And this is what we were talking about, the differential change. How much did x change? It changed by 0.1. So how much is this going to change from 6? 0.1 times the slope. So f of 3.1 is approximately equal to 6 plus 1 plus e cubed over 9 times 0.1. And then it's just a matter of chucking that into your calculator. And it's about 6.234.
B as well.
B, all right.
They're wrong.
So to find f double prime of x, we're going to need to use the quotient rule. So that'll be x squared times the derivative of the numerator, which is just e to the x, minus the numerator, 1 plus e to the x, times the derivative of the denominator, which is 2x, all over x squared squared, so x to the fourth. There's very little to be gained by trying to simplify this because it just asks us for the value. The other thing is that you can do this without doing any of that. Why? Because it gave you f prime and it asked you for its derivative at 3. So we have a function and we want its derivative at a point. That's the numerical derivative. You can just do that straight up on your calculator.
That's what I did. I got 0.7.
You got 0.7? Well, you rounded it way too much. 3 decimal places is the minimum amount of accuracy you have to give. Right?
That's my problem.
You may have done it absolutely correctly. Just, crazy rounding. So the numerical derivative of, hang on a second. 1 plus e to the x over x squared, evaluated at x is equal to 3. What have I done wrong?
That's d over dy.
Why is it d over dy? What the heck? Hang on just a second.
You said it's a dy. Like when you were typing it.
Oh, well, how did I get y? No, I mean, seriously,
I don't know.
I'm pretty sure I typed.
I don't, you had alpha already pressed and then you answered a y.
I don't even know where y is.
It's the 1.
Okay,
I got it. I got the answer.
you're good?
Yes, sir.
That was bizarre. I'm like, wait a minute, how did those y's get in there? Well, we can play back the tape later and see. What did he punch? Anything else?
No.
Okay, so those are all old AP exams questions. Okay, so you can see the kinds of things that get asked about. They're not going to ask you to find the linearization. They're going to say find the equation of the tangent line and use it to do something. Okay, but it's the same thing. And I really like this idea. For me, this very much helps. Where did it start? What's the rate of change? How much did we change? Thinking about it that way is helpful. And when we get to the fundamental theorem of calculus in a few weeks, thinking that way is going to be helpful again. And then when we get to doing series, thinking like that's going to be helpful again. So start thinking in that terms. This is where we started. This is the rate of change times how much the change was in the input. Okay, we're actually going to eventually expand that to an infinite polynomial. So, all right, let me give you today's notes.
I go grab my water bottle quick. I'll have 50% faster.
Nope. Yeah,
I'll do it.
that's a good idea.
Which class? Physics?
No, I was sitting in the water bottle.
It's in the where?
It's not water.
Waterburger?
Waterfall. Is that what they
Oh,
call it?
waterfall?
The fountain, the fountain.
The water fountain?
I don't know what they call it.
Okay.
It's just some people say fountain.
That seems a little overly formal to me. All right. So today we start related rates. This is an application of the derivative. Basically, if you have a quantity that changes over time, and it's related to some other quantities by an equation, then if you take the derivative with respect to time, you relate the rates. You know, what is the rate of change of this one over time? What is the rate of change of this variable over time? So let's take a look. This one has been in every calculus book that I have ever looked at, or one very similar to it. And on a personal note, I lived this once, almost 25 years ago. Me and a ladder leaned against the wall, and down we came. Yeah. If you ever see me limp after sitting down for a while, it's because it still hurts.
What did you break?
Everything. So your hands, if I'm using my hand like my foot, there's two sets. In your hand, there's just one set of bones here. There's two sets. And the one nearest my toes went up over the other set. So they were double stacked.
Exciting.
And then if you feel your ankle, then just a little bit past that, further down your foot is another hard spot. That's your navicular. That snapped in half. And on the other side, if you feel on your hand, there's a bone that sort of right here sticks out just a little bit. You have one like that on your foot. The tip of that bone broke off. This they didn't fix. The navicular, they put a screw into it to hold it in place. And they did surgery where they pushed these back down, pushed them in place, and put pins in to hold them in place for, I don't remember how long, several months. And then once they heal, you can pull the pins out. Actually, pulling the pins out doesn't hurt because you don't have any nerve endings inside the bones. So, and what happens is once they heal, it kind of calcifies around it, and that's how you know it's ready to pull the pin out if you can pull them out easily. If you can't pull them out easily, they're not healed yet. So anyway.
Some announcement I just was going on, but phones don't work.
So that makes the announcements pretty useless.
Yeah.
All right. So a 16-foot ladder is leaned against a building. All right. You need diagrams for these. They don't need to be anything particularly good, but you do need diagrams. So we always assume that buildings stand straight up and down and that the ground is level and flat. Why are people going places?
I think that's what the announcement was.
Was that for the bell?
So it should have like 10 more minutes for the bell.
2:02?
So 10.
Yeah, we've got another 10 minutes. We'll at least get through an example.
It's probably like cheer or something to get ready for the pep rally.
Oh,
That's my guess.
don't get me started. All right, so the ladder leans against the building like so. The ladder doesn't change length, so put the length on it. Anything that changes gets a variable. So, in this diagram, this distance is changing. So let's call it y. Let's call this x. Both of those are changing over time. Okay? So it says, if the foot of the ladder is being pulled away from the building at a rate of 3 feet per second, let's stop there. Here's the foot of the ladder. It's the bottom of the ladder. That means x is increasing at a rate of 3 feet per second. So dx dt, the change in x with respect to time, is 3 feet per second. And they want to know how quickly is the top of the ladder sliding down. So we want to know how fast is this distance changing. So what is dy dt? At a particular, it's almost always at a particular time when the foot of the ladder is 8 feet from the building. So when x equals 8. So we need an equation that relates these variables. It's a pretty simple one. Oh, don't everyone jump at once. It's a right triangle.
Oh, aggregate.
Thank you. So x squared plus y squared is equal to 16 squared. And what we'll do is we'll just take the derivative of this with respect to time. So that'll be 2x dx dt plus 2y dy dt equals, be careful here, 0. 16 squared is just a constant. So I can substitute in the things that I know. I'm interested in dy dt. I know that x is going to be 8, so it's going to be 2 times 8 times dx dt is 3 plus 2 times, and this happens a lot. You get to a point and you're like, wait a minute, I don't know what y is. You calculate. You go back and do this equation again. For those of you who remember such things, if the short leg is half the hypotenuse, 30, 60, 90 triangle.
The square root of 3 times 8.
Yep, it's 8 squared is a 3. Or you can do the Pythagorean theorem. Either is fine. Times dy dt is 0. I'm going to divide both sides of the equation by 8 to simplify this. I can divide both sides by 8 as well, right? I said 8, I meant 2. I was thinking to the next step, my fault. So that means that the square root of 3 dy dt is going to be equal to negative 3. So dy dt is negative 3 over the square root of 3 feet per second. Quick, by the way, on this, if you pull this out at a constant rate, the rate at which the end of the thing is going down approaches infinity. It's going down faster and faster and faster, which is a pretty interesting experience, let me tell you. All right. The other question that was asked on this one is, how fast is the angle formed by the ladder and the ground changing? Well, here's the ladder and here's the ground. So that's theta. So I need something that relates this angle to some other quantities. Since we know the most about x, I'm going to do cosine. because x is adjacent and 16 is a constant, is the hypotenuse. So the cosine of theta is x over 16, which means that the derivative of cosine, being negative sine of theta, times d theta dt, which is what we're looking for, is equal to 1/16 dx dt. So then, well, I know dx dt is 3. Problem is I don't know sine of theta, but at the time in question, we already calculated that this was 8 square roots of 3. So sine will be 8 square roots of 3 over 16. This will be negative 8 square roots of 3 over 16 times d theta dt. So let's see, let's cancel that, make that 2. I'll multiply both sides by negative 2 over the square root of 3. And we get that d theta dt is equal to 3/16 times negative 2 over the square root of 3, which is negative square root of 3 over 8. And that would be radians per second. Let's see if we can get the next one at least started. I knew the problem with the way the bells work during this time is just, actually let's skip that one. Let's do this one.
7th and 8th period are a lot shorter than the other ones.
Yes, the other ones get shortened by a minute. These get shortened by like 12.
Yep.
All right, water's pumped into a conical tank, point down. And you're like, really? Is there such a thing? Well, most of the time they're not a cone because the bottom is cut off. Whose radius is 8 meters and whose height is 12 meters. I actually draw the height outside and you'll see why in just a second. Water is entering the tank at a rate of 15 cubic meters per minute. Let's stop there. What the heck does that mean? So it's a rate, so it's got to be a derivative. The derivative of what? With respect to what? Well, that's told to you right here. Cubic meters per minute.
Oh, water, man.
So volume with respect to time. So dV dt, and water's entering, so this is going to be positive, is equal to positive 15 cubic feet per minute. How fast is the water level rising? All right, the water level is actually down here someplace. We'll call that quantity H. So I want to know, what is dH dt when the water's 3 feet deep, when H is 3? The formula for the volume of a cone is?
It's 1/3 times pi r squared, pi r cubed.
Pi r squared times height. And we could take the derivative of this with respect to t just like it is. And there are times when you have to. However, the radius of this water, the ratio of the radius to the height is the same as the ratio of the radius to the height of the whole thing. So I'd like to get h in terms of r. So h is to r as 12 is to 8, which is 3 to 2. So the height is 3/2 of the radius at all times. So I'm going to substitute that in and simplify. And that's going to give me 1/2 pi r cubed is the volume. So then dv dt, taking the derivative with respect to time, is 3/2 pi r squared dr dt. So that's 3/2 pi times, oh, I did this all in terms of r, didn't I? What should I have done? Should have done it all in terms of h. That would have been better.
Oh well.
Well, so r is equal to 2/3 h, right?
Yeah.
So the volume is 1/3 pi r squared times h. So it's 1/3 pi 2/3 h squared times h. So it's pi over 3 times 4/9 h cubed. So now dv dt is going to be pi times 4/9 h squared dh dt. I multiplied the 3 times the pi over 3. And you would just substitute in what you know. This is 15 pi 4/9 h at the time in question is 3 times dh dt. Solve that for dh dt. It's 15 over 4 pi. Feet per minute. Okay. There are some other examples in your book. You may want to look at those if you come up against anything that you're like, I don't understand that. Look at the examples in the book as well. Yes, sir.
Nothing.
Okay. Y'all have a great weekend. And I look forward to seeing all of you on Tuesday.